The National Electrical Code, referred to as NEC, requires that the minimum size service conductors be calculated using the general lighting load and the connected load. The general lighting load is calculated at 3 volt amps per square foot for the first 1000 square feet, plus 1 volt amp per square foot for each additional square foot over 1000 square feet. The connected load is the sum of the nameplate ratings of all appliances and equipment in the dwelling. Consider a question that states the following appliances are included in the calculation. Firstly, a 12 kilowatt range operating at 120/240 volts. Secondly, a disposer rated at 6 amps at 120 volts. Thirdly, a dishwasher rated at 9 amps at 120 volts. Fourthly, a trash compactor rated at 10 amps at 120 volts. And fifthly, a hot water storage tank rated at 4.5 kilowatts at 240 volts. The question also notes that the small appliance and laundry load should be included in the general lighting calculation. However, the question does not specify whether a dryer is included in the load. Section 220.54 of the NEC states that if a dwelling has a dryer circuit, the dryer load shall be included in the calculation of the general lighting load. However, this requirement only applies if a dryer circuit is specified. Since the question does not specify whether a dryer is included in the load, it is optional to include the dryer load in the calculation. Regarding arguments, section 220.82 is part of the optional feeder calculation and does not apply to the general lighting calculation. Section 210.52F lists the required branch circuits for various appliances and equipment, but does not provide guidance on feeder calculations. Based on the available information, it is reasonable to include the dryer load in the calculation of the minimum size service conductors, even if it is not specified in the question. This is because the NEC requires the inclusion of a dryer load in general lighting calculations for dwellings that have a dryer circuit. It is recommended that you consider the following points. Firstly, Section 220.54 of the NEC requires the inclusion of a dryer load in the general lighting calculation if a dryer circuit is specified. Secondly, since the question does not specify whether a dryer is included in the load, it is optional to include the dryer load in the calculation. And thirdly, including the dryer load in the calculation will result in a more conservative estimate of the minimum size service conductors. Let's delve into the specific calculations involved in determining the minimum size service conductors for a single-family dwelling, considering the dryer inclusion debate. The process involves several steps, starting with calculating the general lighting load, then accounting for small appliance and laundry circuits, and finally factoring in the fixed appliance loads. We'll explore each of these steps in detail. Firstly, calculating the general lighting load. As per the NEC, we calculate the general lighting load based on the square footage of the dwelling. The NEC specifies 3 volt amps per square foot for the initial 1000 square feet and then reduces it to 1 volt amp per square foot for any additional square footage. In this scenario, with a 4000 square foot residence, the calculation proceeds as follows. Firstly, for the first 1000 square feet, we have 1000 square feet multiplied by 3 volt amps per square foot, which equals 3000 volt amps. Secondly, for the remaining 3000 square feet, we have 3000 square feet multiplied by 1 volt amp per square foot, resulting in 3000 volt amps. Therefore, the total general lighting load amounts to 3000 volt amps plus 3000 volt amps, equaling 6000 volt amps. This value represents the baseline power demand for general illumination within the residence. Secondly, adding small appliance and laundry loads. In addition to the general lighting load, we must account for the small appliance and laundry circuits. The NEC mandates a minimum of 2 20-amp small appliance branch circuits and 1 20-amp laundry circuit. Each 20-amp 120-volt circuit is considered to have a load of 2400 volt amps. Therefore, the calculation is as follows. Firstly, 2 small appliance circuits contribute 2 multiplied by 2400 volt amps, totaling 4800 volt amps. Secondly, 1 laundry circuit adds another 2400 volt amps. Consequently, the combined load for small appliance and laundry circuits equals 4800 volt amps plus 2400 volt amps, which amounts to 7200 volt amps. This value represents the anticipated power demand from these essential convenience circuits. Thirdly, factoring in fixed appliance loads. Next, we incorporate the fixed appliance loads, considering that the question specifies the inclusion of a range disposer, dishwasher, trash compactor, and hot water storage tank. To do this, we need to convert all loads into volt amps for consistency. Firstly, the range is rated at 12 kilowatts, equivalent to 12,000 volt amps. According to NEC guidelines, ranges can often be calculated at a demand factor lower than the nameplate rating, especially for smaller ranges. For a 12 kilowatt range, we can refer to NEC table 220.55 to determine the appropriate demand factor. Assuming a demand factor of 8 kilowatts, or 8,000 volt amps, we use this value for our calculations. Secondly, the disposer is rated at 6 amps at 120 volts, resulting in 6 amps multiplied by 120 volts, equaling 720 volt amps. Thirdly, the dishwasher is rated at 9 amps at 120 volts, leading to 9 amps multiplied by 120 volts, equaling 1080 volt amps. Fourthly, the trash compactor is rated at 10 amps at 120 volts, resulting in 10 amps multiplied by 120 volts, equaling 1200 volt amps. Fifthly, the hot water storage tank is rated at 4.5 kilowatts, equivalent to 4500 volt amps. Summing these fixed appliance loads, we get 8000 volt amps plus 720 volt amps plus 1080 volt amps plus 1200 volt amps plus 4500 volt amps, totaling 15,500 volt amps. This value represents the combined power demand from these permanently connected appliances. The dryer inclusion debate arises from the ambiguity in the question, as it does not explicitly state whether a dryer is present in the dwelling. If we assume the presence of a dryer, as many residences do have one, we must include its load in the service conductor calculation. According to NEC section 220.54, a dryer is to be calculated at 5000 volt amps of the nameplate rating, whichever is higher. Since no nameplate rating is provided, we use the standard 5000 volt amps. Without dryer, the total load without a dryer is the sum of the general lighting load, small appliance and laundry loads, and the fixed appliance loads. This is calculated as 6000 volt amps plus 7200 volt amps plus 15,500 volt amps, totaling 28,700 volt amps. With dryer, if we include the dryer load, we add 5000 volt amps to the previous total. This is calculated as 28,700 volt amps plus 5000 volt amps, totaling 33,700 volt amps. After obtaining the total volt amp load, we calculate the service current at 240 volts. The formula to determine the current is current equals power divided by voltage. Without dryer, the current is 28,700 volt amps divided by 240 volts, resulting in approximately 119.58 amps. With dryer, the current is 33,700 volt amps divided by 240 volts, resulting in approximately 140.42 amps. Based on the calculated service current, we can determine the minimum size service conductors required. We refer to NEC table 310.16 to select the appropriate conductor size based on its ampacity. Without dryer, for a service current of approximately 120 amps, we would typically use a conductor with an ampacity of at least 120 amps. According to NEC table 310.16, a 1/0 American wire gauge copper conductor with 75 degrees Celsius insulation is suitable, as it has an ampacity of 120 amps. With dryer, for a service current of approximately 140 amps, we would need a conductor with an ampacity of at least 140 amps. According to NEC table 310.16, a 2/0 American wire gauge copper conductor with 75 degrees Celsius insulation is suitable, as it has an ampacity of 135 amps, which might require upgrading to a 3/0 American wire gauge copper conductor with 75 degrees Celsius insulation with an ampacity of 155 amps depending on local codes and specific insulation conditions. NEC Section 310.15 addresses ampacity correction factors for ambient temperature and the number of current carrying conductors in a raceway or cable. These factors must be applied if the installation conditions deviate from those specified in NEC Table 310.16. Temperature correction if the ambient temperature exceeds 30 degrees Celsius or 86 degrees Fahrenheit, a temperature correction factor must be applied to reduce the conductor's ampacity. The correction factors are provided in NEC Table 310.15. Number of conductors if the number of current carrying conductors in a raceway or cable exceeds 3, adjustment factors from NEC Table 310.15 must be applied. These factors reduce the allowable ampacity of the conductors to prevent overheating. In the service entrance calculation, the grounded neutral conductor is generally not considered a current carrying conductor. Overcurrent protection: the service conductors must be protected by an overcurrent device, such as a circuit breaker or fuses, size according to the conductor's ampacity. The overcurrent device protects the conductors from overload and short circuit conditions. With that dryer, a 125 amp overcurrent device would be suitable for the 1/0 American wire gauge copper conductors, provided that the calculated load does not exceed 80% of the breaker's rating for continuous loads. With dryer, a 150 amp overcurrent device would be required for the 3/0 American wire gauge copper conductors, again ensuring that continuous loads do not exceed 80% of the breaker's rating. Grounding and bonding: proper grounding and bonding are essential for electrical safety. The service equipment must be grounded to a grounding electrode system, and all metallic enclosures and non-current carrying metal parts must be bonded together to create a low impedance path for fault current. The grounding electrode system typically consists of a grounding electrode conductor connected to a metal underground water pipe, a ground ring, or ground rods. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. Local amendments: local jurisdictions may have amendments to the NEC that affect the service conductor calculation. It is essential to consult with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations. This may include specific requirements for conductor sizing, overcurrent protection, grounding, and bonding. In summary, calculating the minimum size service conductors for a single-family dwelling involves several steps. Firstly, determining the general lighting load based on the square footage of the dwelling. Secondly, including the small appliance and laundry loads. And thirdly, factoring in the fixed appliance loads. The inclusion of a dryer load is optional if not explicitly specified in the question, but it is generally recommended to include it for a more conservative estimate. After calculating the total volt-amp load, the service current is determined, and the appropriate conductor size is selected based on NEC Table 310.16, considering ampacity correction factors and overcurrent protection requirements. Proper grounding and bonding are essential for electrical safety. Finally, it is crucial to consult with local authorities to ensure compliance with all applicable codes and regulations. This comprehensive approach ensures a safe and compliant electrical service installation in the dwelling. In addition to the core calculations, several advanced considerations can refine the accuracy and safety of service conductor sizing. These include demand factors for various appliances, voltage drop calculations, and future load considerations. Demand factors allow for a reduction in the calculated load based on the likelihood that not all appliances will operate simultaneously at their maximum rated capacity. The NEC provides demand factors for various appliances and equipment in Article 220. For example, NEC Table 220.55 provides demand factors for household ranges and ovens. These factors can significantly reduce the calculated load, especially in dwellings with multiple large appliances. However, it is essential to apply demand factors judiciously and consider the specific usage patterns of the dwelling. Voltage drop occurs when electrical current flows through a conductor, causing a reduction in voltage at the load end. Excessive voltage drop can lead to poor performance of appliances and equipment, as well as potential safety hazards. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders and services. To calculate voltage drop, the following formula can be used. Voltage drop equals current multiplied by resistance. The resistance of the conductor depends on its material, size, and length. The calculated voltage drop should be compared to the allowable limits, and the conductor size should be increased if necessary to reduce the voltage drop. It is prudent to consider future load growth when sizing service conductors. Dwellings often undergo renovations or additions, which can significantly increase the electrical load. It is advisable to oversize the service conductors to accommodate future load growth and avoid the need for costly upgrades later on. A general rule of thumb is to add 25% to the calculated load to account for future expansion. However, the actual amount of oversizing should be based on a careful assessment of the dwelling's potential future electrical needs. The NEC provides guidelines for calculating the interrupting rating of service equipment, such as circuit breakers and fuses. The interrupting rating is the maximum fault current that the equipment can safely interrupt without causing damage or creating a hazard. The available fault current at the service entrance depends on the utility supply capacity and the impedance of the service conductors. It is essential to calculate the available fault current and select service equipment with an interrupting rating that is equal to or greater than the calculated value. This ensures that the equipment can safely interrupt fault currents and protect the dwelling from electrical hazards. Coordination is the selective tripping of overcurrent devices to isolate a fault and minimize the impact on the electrical system. Coordination is achieved by selecting overcurrent devices with different time current characteristics such that the device closest to the fault trips first, while upstream devices remain closed. Proper coordination improves the reliability and safety of the electrical system and prevents unnecessary outages. Coordination studies can be performed by qualified electrical engineers to ensure that the overcurrent devices are properly coordinated. The service entrance conductors must be physically protected from damage and environmental factors. The NEC specifies various methods for protecting service entrance conductors, such as using rigid metal conduit, intermediate metal conduit, or electrical metallic tubing. The choice of protection method depends on the specific installation conditions and the level of protection required. The conductors must also be protected from exposure to sunlight, moisture, and corrosive substances. The service equipment must be readily accessible for maintenance and inspection. The NEC requires that service equipment be located in a readily accessible location and that sufficient working space be provided around the equipment. The working space must be clear of obstructions and must be large enough to allow for safe and convenient maintenance and inspection. The service equipment must also be properly labeled to identify its purpose and function. Proper labeling helps to prevent confusion and errors during maintenance and troubleshooting. The NEC requires that all electrical work be performed by qualified individuals who are trained and experienced in electrical safety. Electrical work can be dangerous, and it is essential to hire qualified professionals who can perform the work safely and in accordance with the applicable codes and regulations. Unqualified individuals should not attempt to perform electrical work, as this can lead to serious injury or property damage. The electrical installation should be inspected by a qualified electrical inspector to ensure compliance with the NEC and local codes. Electrical inspections help to identify potential safety hazards and ensure that the installation is safe and reliable. The electrical inspector will review the installation and verify that it meets all applicable requirements. Any deficiencies found during the inspection must be corrected before the installation is energized. The NEC is a complex and comprehensive document, and it is essential to stay up to date on the latest revisions and interpretations. The NEC is updated every 3 years, and it is important to review the latest edition to ensure that your electrical work is in compliance. The NEC also publishes interpretations and clarifications to address specific questions and issues. Staying informed about the latest changes and interpretations helps to ensure that your electrical work is safe and compliant. The service conductor calculation is a critical aspect of electrical design and installation. A thorough and accurate calculation is essential for ensuring the safety and reliability of the electrical system. By considering all applicable factors and following the guidelines of the NEC, you can ensure that the service conductors are properly sized and protected. Remember to consult with qualified professionals and local authorities to ensure compliance with all applicable codes and regulations.